Chapter 2 is about the beam and plate bending problem, and we're going to derive the beam bending equation now. So we're thinking of a rigid beam that resists being bended, unlike a string, which we'll talk about in chapter 8. String resists being stretched, but it doesn't resist bending. This is a rigid beam that doesn't like to bend. It's an elastic beam, so it will bend, but it doesn't like to. And we're going to derive the equation for the height of the beam. U of x is the height of the beam above the table or whatever. And the total energy in the beam is the bending energy plus the energy done, work done against force Q. So there's an external vertical force, which may just be the weight of the beam itself, but function of x, force per unit length along the beam, acting on the beam. And this is the bending energy because it's proportional to the second derivative squared. So if the beam is, I'm not going to prove that this is the energy, but to make it reasonable here, if the beam is straight, whether it's flat or not, if it's straight line, then the second derivative will be 0, and there's no bending energy. And the second derivative is a measure of the curvature, and the bigger the second derivative is, the more it's bent, and the more the energy is. D is could be a function of x, bending stiffness. The stiffer the beam is, the more it resists bending, the bigger D is. And then this is the work done against the force Q. Like if U is in the opposite direction of Q, this will be positive, and the force Q times dx, that's the force acting on a little piece dx. If you move direction U against that, the total work is the distance you move times the force. So that hopefully makes it reasonable that that's the energy anyway of a beam. And we're going to have boundary conditions on each side. We have that U and U prime are given, that the x equals 0 and x equals L, the two ends of the beam. The height and the slope of the beam are given. So it's called a clamped. These are clamped in conditions. Basically think of the beam as being stuck in the wall on both ends, and not only the height but the slope is fixed by how it's stuck in the wall. Okay, so the true solution is going to be the one that minimizes the energy. So how do we find an equation satisfied by U? So if U of x is the function which minimizes its energy subject to these four conditions, if we take any other function E, which is 0 at both ends and 0 derivative at both ends, then that means if you take U plus any multiple of E, that U plus alpha E still satisfies the four boundary conditions. Therefore, the energy of that function must be greater than or equal to the energy of U if U minimizes the energy. So alpha of alpha, defined as E of U plus alpha E, has a minimum at alpha equals 0 because this is minimized when alpha is equal to 0. Any other alpha, the energy is going to be greater. So what is the energy at U plus alpha E? Remember, U and E are functions of x. Alpha is a scalar. Well, just replace U by U plus alpha E here and here. Take the derivative with respect to alpha. There's alpha, so the derivative with respect to alpha, 1/2 times 2 cancel, you get D times U double prime plus alpha E double prime times the derivative of this with respect to alpha, which is E double prime. Derivative of this with respect to alpha is just minus EQ. And then you plug in alpha equals 0 and that term disappears, and this is what has to be 0 because the alpha has a minimum at alpha equals 0, therefore the derivative of alpha with respect to alpha at 0 must be 0. So that has to be 0. Now we're going to do two integration by parts. I'll skip the details here, but this is just ordinary integration by parts. We're going to take two derivatives off of E and put them over here. The EQ, we don't touch that. So we end up with just E here, and D U double prime has two more derivatives. Then we have these four extra terms that come from the integration by parts. But notice that since E is 0 at both ends and E prime is 0 at both ends, all four of these terms disappear, so you get this. And now you can factor E out of that, and that integral must be 0. So here we are, we factored E out of that. And since E is an arbitrary function in the interior, it satisfies the four homogeneous boundary conditions, but in the interior it can be anything. So if you have the integral of something times a totally arbitrary function, if that's 0 for all totally arbitrary functions, the only way that can happen is if this function is 0, and there's your differential equation. So this thing here, d u double prime quantity double prime minus q, must be 0. So there's our beam equation, and notice it's fourth order, which is unusual. I believe that's the only fourth order equation in this book. And we assume boundary conditions that u and u prime are given at both endpoints. Those are clamp boundary conditions. But if you look at the previous page, you'll see that if u double prime is 0 at either or both endpoints, or d u double prime quantity prime is 0, then you also get rid of these terms. And so those are possible boundary conditions also. So as for boundary conditions then, if u and u prime are given, the way I've got it drawn here, u is 0, assuming this is u equals 0 line here, and u prime is 0, but they could be clamped higher up and with a different slope, but those are clamp boundary conditions. And so the flagpole is stuck in the wall as clamp boundary conditions. Q is the external force. If Q is negative, for example, the weight of the beam could just be negative constant. These are called clamp boundary conditions. Those don't have to be 0, but whatever they are. And if U is given and U double prime is 0, those are called simply supported boundary conditions. That means it's not clamped, so the derivative's not fixed, but the height is fixed, but not the derivative. The derivative is free, so U and U double prime are 0. Well, U doesn't have to be 0, but U is something, and U double prime has to be 0. Those are called simply supported boundary conditions. Or you can have, if you stick the flagpole in the wall and you don't support it or anything, it's just free out here, then those boundary conditions would be U double prime equals 0 and D U double prime quantity prime equals 0. And normally D will be a constant stiffness, which means the third derivative is 0. So free and unsupported usually just means the second and third derivatives are 0 out here. So there's those three different kinds of boundary conditions: free and unsupported, simply supported but not clamped, and clamped. And the next section derives the plate bending problem, and it's very, very similar to the beam bending problem, except that it's two-dimensional, which makes it a little more complicated. But again, we start with the energy being, instead of u double prime squared, it's Laplacian of uxx plus uyy squared. And there's the work done against the force Q of x and y. So it's very similar. We won't go through this, but it's almost exactly the same, except it's a multivariate case. So you're going to have to use, you're going to do two integration by parts again, but now it's going to be a multivariate integration by parts. And Appendix A has some important formulas that we'll use throughout the course, multivariate calculus. So let's look at that. There's also a link on your class webpage to a copy of this, basically. So let's look at Appendix A. So here's Appendix A. This is actually written for three-dimensional derivatives, but it's obvious what you do with 2 dimensions. You just get rid of the third thing here. So the gradient of U is, well, you know what the gradient is, divergence. If you think, you should review this sheet here. If you just think of del as being this operator here, then del u makes sense. Just think of this times a scalar u. It's not really times, but it looks like it is. And the divergence is like a dot product of del with vector v, So u is a scalar function, v is a vector function, and that'd be this times that, plus this times that, plus this times that. It's not really times, but symbolically that works. And so divergence of the gradient of u would be Laplacian of u, uxx plus uyy plus uzz if it's three-dimensional. Okay, the divergence theorem, that's the most important thing. That's basically the two- or three-dimensional equivalent of the fundamental theorem of calculus, so it's critical. It says the integral over the entire region of the divergence of a vector function v is equal to the integral over the boundary of v dotted with n. And see if the interval, if it's a one-dimensional equivalent here, that just means the derivative of the scalar function v integrated from a to b is the integral over the boundary, which is just 2 points, a and b, of v times n is 1 at the b and minus 1 at the other. So this makes sense. If you look at one dimension, it's just a generalization, but you just need to remember this, the integral of the divergence. It converts a area or volume integral into a boundary integral. And what we're actually using in deriving these, the plate bending problem, is the two-dimensional integration by parts. This is the multi-dimensional equivalent of integration by parts. U times the derivative of v is equal to uv minus the integral of derivative of u times v. That's what it would be in one dimension anyway. So anyway, we won't go through the details for the plate bending problem, but that's basically the formula that's used, and it's used twice. So the plate bending derivation of plate bending problem is almost exactly analogous, just generalized to two dimensions. There's the energy. Again, you say, well, if you're assuming clamped boundary conditions, that means that u on the boundary, now this is a whole, not just 2 points, but an entire boundary of the plate, u and the normal derivative of u are given, and then you take any e which is 0 and normal derivative 0 on the boundary, then again e of u plus the energy of u plus alpha e has to be greater than or equal to u. Alpha of alpha is that. Take the derivative back to alpha, set it to 0, do two integration by parts, and you end up with essentially what you might expect for two dimensions. It's the Laplacian. That's Laplacian of u is uxx plus uyy. It's kind of a generalization of second derivative of d times the Laplacian of u is equal to q. So pretty much what you'd expect. And again, you can have clamped boundary conditions where u and the normal derivative are 0. So basically the edge of the plate is clamped, stuck in a wall somewhere. Or you can have free and unsupported boundary conditions, or you can have simply supported boundary conditions where u is given, but it's not clamped, so the derivative of u with respect to normal is not given, but the Laplacian is 0. That's for free and unsupported. Okay, we're going to work through both example problems here. First, there's a beam bending problem, a beam of length 2.5. There's a constant uniform weight, which it's probably just the weight of the beam itself in the downward direction, gravity. So Q is just constant -1, D is constant 10. And at the left end point, it's clamped, so U and U prime are 0. But at the right end point, we have the second and third derivatives are 0. D is constant, so that's just third derivative. That's free and unsupported. So basically, it's a flagpole that's stuck in the wall horizontally at the left, and it's just totally free at the right end point. So now PD2D will not solve fourth order problems directly. You have to break a fourth order problem into two second order problems. So we're going to define M to be D times second derivative of U, called the moment, and then the second derivative of M will be Q. So that's equivalent to, you know, since m is basically d times u xx, this says that d times the fourth derivative of u is equal to q. And m, which is the second derivative, well, divided by d, is 0, and its derivative is 0. In other words, the second derivative of u and the third derivative of u are 0, which means the moment and the derivative of moment are 0. So there's your two differential equations and for boundary conditions. And now we're going to solve this. We could, if we could use either collocation or Galerkin. I'm going to use collocation, so I could use the GUI, but I'm not. I'm going to use the interactive driver. We've done a couple examples of the GUI already. So let's solve this problem with collocation and the interactive driver. So here we go. PD2D, call it EX1, example 1. And it's going to start asking questions. Do I want to do one of their prepared examples? No. The dimension of the problem, remember that doesn't count time. Well, there's no time here anyway, but it's a one-dimensional problem. Galerkin or collocation, I could actually use either one, but I said I was going to use collocation. Double precision, yes, always. A lot of the questions, they have what's called a fine print, and it says if you don't want to read the fine print, which you usually don't, especially starting out, just default it and don't worry about it. So default means hit return. And now we want to define some parameters. Whoops, I went past the parameters. Well, we'll define them later on. If you don't want to read the fine print, enter no. I meant to enter some parameters, L and D, but I can do it later. Okay, so how many grid points? Well, that's kind of arbitrary, but the bigger you take this, the more accurate it'll be and the more work, but it's one-dimensional, so it's not going to take much work anyway. So let's say 21 grid points. It's going to be uniform grid by default. You can make it non-uniform if you want, but we don't. And we're going to start at 0 and go out to L, which is 2.5. I'm just going to put in the 2.5 since I failed to enter that as a parameter. Steady state, yeah, there's no time. Is it linear? Yes. Two equations, and the unknowns we're going to call R, and I can't call it M. See, if I try M, it'll say, no, we can't use I through N, because those will be Fortran variables. The integers and your functions can't possibly be integers. So I'll call it RM. So our variable is going to be U and RM, which is basically M. And do you want to calculate the integral of something? Yes, I do. I want to calculate the integral of the error. One integral. So I want to integrate the absolute value of u minus the true solution, which I'm going to have to define later on. So I'm going to define the true solution in the Fortran function true of x. I don't want any boundary integrals. That's only 2 points in the boundary. Okay, so now here's your two differential equations. And remember, the two equations are d times uxx minus is equal to m. And I would normally just put a d in here, but I forgot to define the d, so I'm going to have to put a 10 times uxx minus m. And the other one is going to be mxx equals minus 1, because remember q is a constant minus 1. It could be a function of x here, but it's constant. So the second equation was mxx equals q. Q is minus 1, so taking everything on one side, that's F2. So that should be our two differential equations. Do we have periodic boundary conditions? No. Okay, the boundary conditions, remember at the left-hand point, it was clamped, so U and UX were 0. The right-hand point was free and unsupported, which means the second and third derivatives of U are 0, but you can't write that the boundary conditions can't involve second or higher derivatives. They have to be first derivatives or lower, but remember that was just M and MX. The second derivative, U is, if the second derivative is 0, M is 0, third derivative 0 makes M sub x 0. So there's our 4 boundary conditions. And we're almost done here. We default all these things here. Okay, the grid, output grid, this is not related to accuracy. This is just for the plot. The output plots will make 50 grid points, and that's just if you want to zoom in. If you want to do any plots, the GUI will just automatically decide what plots to do for you. It won't ask you as many questions, but it doesn't give you as much flexibility. So I'm going to do a cross-sectional plot of U. Call it title be U, and we're essentially done, except for that. Remember, we defined a function true of x, which is going to have the true solution. Well, the book gives the true solution. And at this point, I can say, it says, do you want to define any Fortran functions? I can do that here, or you can do it later in the Fortran. So I could just say no and add it with an editor, or I'll show you another way of doing it. It might be even easier, but I'm just going to go ahead and add it here. And so it says, okay, now start typing to define any functions that you defined, that you used earlier. So here's where you have to know a little bit of Fortran. See, true of x. Remember, this is a useful thing to have, which we're using double precision. This line here, we nearly always put in your functions. And what is true, it's going to be, well, just read it from the book. The exact solution is not that hard. It's just basically fourth derivative of U equals the constant. And so you take integrate 4 times and apply the boundary conditions, and you can easily find the solution. But in the book, it's given as minus 0.1 times x to the 4th power divided by 24 minus L, which is 2.5 times x cubed divided by 6 plus L square times x squared divided by 4. There's a very good chance of making an error here, but we can correct it easily with an editor. Return and end, and we're done. Okay, we're ready to run it. The odds are it won't work the first time, but let's try it anyway. Might get a compile error if there's a compiler error here. So we just run PD2D EX1 and see what happens. What do you know? There's the error is 10 to the minus 7, so it's working perfectly. And let's look at the output, the plot of the height of the beam. And there it is. So it's clamped. U is 0 and U prime is 0 here. And the right hand side, it's free and unsupported, so the flagpole's just hanging out there. And it's going down because of the weight of the beam. There was an external force due to the weight of the beam itself that's pushing it down. So all of the problems in the book have some way for you to check your answer. They'll either draw a graph of the solution or give you an integral, some integral so that you compare, or the true solution analytically, some way that you can check your work. And this one, the true solution's given. So the error is that small, it must be working. Okay, now I want to do the second example, and this is a plate bending problem. So the well, we're the D, the bending stiffness is 1 to keep it simple here. And so it's a fourth order problem, but we reduce it to 2 second order problems the usual way. The Laplacian of u, that is uxx plus uyy, is equal to m, and then mxx plus myy is equal to q, the external force. In this case, instead of a uniform, the weight of the plate, like the last problem, we've got a delta function. Now, what does that mean? That means that you've got a sharp, you've got an external force that's all concentrated at one point. It's a unit square of length 1 on each side is the plate. So it's a square plate, and right in the middle at 0.5, 0.5, there's a delta function. So basically you've got like a metal plate, and you're ignoring the weight of the plate itself, and you just got a pencil that's pushing down in the middle, and so the external force is a delta function, which is basically infinite at that one point, zero everywhere else, but such that the total integral is 1. You know what a delta function is. It's minus, so it's in the negative direction. So basically it's, think of a square plate, and right in the middle there's a sharp force downward. And boundary conditions, well, we're going to have on 2 of the sides at x equals 0 and y equals 0, we'll have clamped boundary conditions, u and normal derivative of u is 0. You know, at the left, x equals 0, and normal derivative means the y derivative. At y equals 0, the normal derivative is the x derivative, but in either case, it's the normal derivative. So you have clamped boundary conditions on the left and bottom, and simply supported boundary conditions on the top and right, x equals 1, y equals 1. So there u and m, the Laplacian of u, are 0. So u is fixed but not clamped. So there's your boundary conditions, there's your 2 differentially second order equations, and we're going to solve it. Now we have to use the Galerkin method this time because of the delta function. The collocation method doesn't allow you to put in a delta function, and you'll see that the Galerkin method does. There's a reason for that, but in any case, so we're going to have to use the interactive driver again because we have to use the Galerkin method. Okay, here we go again with the interactive driver. We'll call this example 2. Do I want to work through a prepared example? No. If you say yes, it'll give you 15 different examples, and you can look at one of those, and it'll give you not only the answers, but not only the questions, but the answers. But we don't want to do that. Although you should, first time or two you use it, you should probably work through an example using the interactive driver. Like the GUI has 3 examples, prepared examples. If you want to do one of those, the interactive driver has 15 of them. Okay, this is a 2-dimensional problem, and we can't use the collocation method, so we have to use Galerkin. Now, if I make a major mistake here, like if I said it was 3-dimensional, or if I'd said I want to use collocation methods, I just have to start over. If I make a minor problem, I can correct it in the Fortran. So Galerkin method, double precision, yep. Don't want to read the fine print, so default it. Okay, parameters. There really aren't any parameters, are there? So forget that. Okay, now since this is a Galerkin method, we're going to have to define initial triangulation. Fortunately, it's a square, a rectangle. That's real easy. It'll do the triangulation for you automatically. So we'll take option 1, which is that's a rectangle, and then you don't have to worry about the initial triangulation. So option 1 says it's a rectangle, and we just need to give a x grid and y grid, and it doesn't really matter what in x grid and in y grid are, because you can refine the triangulation further anyway. But let's take 5 grid points in each direction. So x goes from 0 to 1, and y goes from 0 2, whoops, 1, and now, okay, the boundary conditions are much more confusing for beginning users for Galerkin than for collocation. But remember, on two sides we have u and the normal derivative equals 0. And on two sides, the other two sides, we have u and m equal to 0. So you have to give a negative arc number to the ones where the unknowns are all given. So basically, if you know your unknowns, they don't have to be constants, but if you know what they are, as functions of the boundary, then you give a negative, the Dirichlet type boundary conditions. So at the top and right, where u and m are both 0, or rm are 0, then we can give negative arc numbers to those. But the left and bottom, where you have more general boundary conditions, you don't know m, you do know u, but you don't know m. If you don't know all the variables u and m, then you have to give a positive arc number, and the boundary conditions are a little more confusing there. So left-hand point, we'll give a positive arc number. Right-hand point have to give a negative arc number. Bottom, positive arc number. I can use the same ones as the boundary condition would be the same. Top, -1. Normally they should be different, but if they're the same boundary conditions, you can get away with giving the same. So we've given the right and top negative arc numbers, the bottom and left positive arc numbers because they're more general. So there's two types of boundary conditions. The Dirichlet are the best ones. All you have to, if you just know u and m, then you can give a negative arc number, and when it asks you for u and m, you can just put in, it doesn't have to be constants, but as long as they're known functions. Otherwise, anything else, even if you know one of the functions on the boundary but not both, then you're going to have to use the more general boundary conditions, which are the confusing ones. Okay, we did a 5x5 grid. That's 4 triangles in each grid, so it's 64 triangles. Let's do a lot more than 64. Let's do 1,000 triangles. So it's going to take my 5x5 grid of triangles and refine it until we have 100,000 triangles. Don't want to read the fine print. That's for a non-uniform grid. More fine print. And if you don't want to read the fine print, this is choosing the linear system solver. That could be important, but 4 is the recommended one and usually the best choice. The degree of the element, heck, let's use 4th degree elements, the highest possible. Steady state, don't want to make a mistake here, you have to try it all over. It is steady state, not time dependent or eigenvalue. Is it linear? Yes. Okay, how many differential equations? 2. And the unknowns are u and rm again. Is the problem symmetric? If you don't know or don't want to figure it out, just say no. So let's say it's not symmetric. In fact, it's not. So symmetry will just save you a factor of 2 time if it's symmetric. But if you say it's symmetric and it's not, you're going to have a problem to get bad results. So let's say no. And if it is symmetric, it won't hurt anything, just slightly a little more inefficient. So we'll say it's not symmetric. Now, do you want to calculate an integral over the whole region? Yes, we do, just because the book tells you that the integral of m square tells you what it is, so that'll be a way to compare. So let's say, yes, we want to do one integral, and we want the integral of m square. So I can compare with the book. Don't want to do any boundary integrals. Okay, here's where you define, here's where the delta function comes in here. It says, do you have any point source terms? This collocation can't do this. And so yes, we do have a direct delta function. How many? 1 at the point 0, 0.5, 0.5. And you have to look, some of these are a little painstaking, but the coefficient of your delta function on the right-hand side of the first function is 0. The coefficient of the delta function on the right-hand side of the second equation is -1. That's what that is. So that's basically telling you that you're going to have 0 times delta of x minus 1/2 comma y minus 1/2. There's the delta function at where it's centered at. And so that it's actually going to, it's not going to be approximating the delta function. It's going to use exactly a delta function. Okay, so now the Galerkin method PDEs look different. They have this divergence form. And remember that the first equation says uxx plus uyy equals m. So A1 needs to be ux. B1 needs to be uy, so that's derivative with respect to x of ux plus derivative with respect to y of uy equals F1, which is m. So the first equation is uxx plus uyy equals m. If there was a collocation, it would be a lot easier. I'd just say uxx plus uyy minus rm equals 0, but have to write it in divergence form, but it's not the big a deal. So F1 will be m, or we have to call it rm, and A1 will be ux. Okay, since Fortran is not case sensitive, it doesn't matter, but I prefer to write it as capital U, small x, looks better. And B is u sub y. So see, that says first equation is derivative with respect to x of ux plus derivative with respect to y of uy equals m. Now the second equation, and notice it says that when you're later prompted for the F's, don't include these. So we've already taken care of the delta function. That's handled separately. So F2 is 0 because that was all there was on the right-hand side. And then we'll have mx and my. See, the second equation says derivative with respect to x of A2, which is mx, so that's mxx, plus derivative with respect to y of my, so that'd be myy equals 0, but, well, really, that doesn't include the delta function here. So now the boundary conditions. So the fixed boundary conditions, do you have any fixed boundary conditions? Yes, at the top and right-hand side, those are both arc numbers -1. And what is u and what is m? They're both 0. So FB1 and FB2 is 0. And actually, I could have just defaulted that. So I could have said, no, I don't have any. It says where you have to specify them. The default is 0. So if I said no, anything with negative arc number is going to default to u and m equals 0. And so, no, I don't have any more. Well, I really had 2, but I'm calling them both -1. So, okay, free boundary conditions. Here comes the hard part. Do I have any free boundary conditions? Yes. On arc number +1. Now, what are the free boundary conditions? Well, this is one of the more complicated things in the course. You look very carefully at these boundary conditions. The boundary conditions for collocation are real simple. You just write them out the natural way. For Galerkin, you have to be careful, and here's the boundary conditions. Here's the more general boundary conditions. Okay, remember that A1 is u sub x, so that says ux nx plus uy ny equals gb1, and the second equation says mx times nx plus my ny equals gb2. Nx ny is the unit normal, outward normal, so this is just the gradient dotted with outward normal, which is the normal derivative. So that says the normal derivative of u is gb1, and that's going to be 0. Okay, that's simple enough because the normal derivative is 0. But now the other boundary condition was, see, if I put gb2 equals 0, that's going to be the left-hand side. Now it's m sub x nx plus m sub y ny. That's the normal derivative of m, and that's not 0. The other boundary condition is u equals 0. So we basically got a mixed boundary condition. That's what makes this confusing, where one of the variables u is known and the other one is not. How do you do that? Well, basically you can just say 1 times 10 to the 20th power times u equals 0, and that's essentially u equals 0. because it doesn't matter what the left hand side is. The right hand side is 10 to the 20th times u. That essentially makes u equal 0, and that'll work just fine. But actually PD2D allows you to just simply write 0 of u, which is going to be exactly the same. See here, so that's how you can mix boundary conditions. If this tells you that the normal derivative is 0, this tells you that u is 0. Okay, we're done with the boundary conditions. We've got all the hard part done here. Essentially done. This is just the output grid. We can use 50 by 50 output grid. That's only if you want to zoom in. And let's do a surface plot. Could do contour plots. Surface plot of u. We're not really interested in m. And we are done. Okay, we're going to try running it again, and good chance it won't work, but we'll fix it if it doesn't. $16,000 unknowns, because a lot of, and there's the integral. Remember, that's the integral of m square, and that's exactly what the book says it is, 0.007426, so it seems to be working fine. Let's look at the plots using Ghost View. Well, there's your initial triangulation. Remember, we had a 5 by 5 grid, and it automatically gets initial triangulation of 4 triangles in each one. And then the final triangulation, that has 1,000 triangles in it. And there's the plot. And it's not real easy to see, but you can see here and here it looks like it's clamped. That is, u is 0 on the entire boundary. The normal derivative is 0 here, so it's clamped. So it's flat there and here, but not there. So that's not really symmetric here, these boundary conditions there. But this is apparently working just fine. Okay, let's talk a little bit about the homework, and we're done. I assigned problem 1, which is just a beam bending problem, and you can use collocation method. In fact, you can use the GUI if you want to, so this one will be fairly straightforward. Then I gave you problem 3A, which is a circular plate with, again, D bending stiffness 1, and you've got a so it's a unit circle this time, and again a delta function right in the middle. So it's a circular plate with a point force pencil, sharp pencil pushing down in the middle, and simply supported boundary conditions. That'll make the boundary conditions easier. Just u and m will be 0, so that you won't have that messy boundary condition like we just had. So again, you define the Laplacian of uxx plus uyy equals m, mxx plus myy equals q, which is minus this delta function. And you're going to solve that with simply supported boundary conditions on the entire boundary. Now, the interesting thing is part B, which I did not assign. I'm going to do it for you. Part B says solve that analytically. It's kind of surprising that you could solve a problem like that analytically, but you can, and I'll show you in a minute. And you can take my solution and use it to calculate the error in your. So I'm going to do part B for you. That's just the analytical solution of part A, so that you can compare your solution with the true solution. And you have to use Galerkin because of this delta function again. I think this is the last time we'll see delta functions in this book. If that were a constant force, you could use collocation and be simpler. Actually, you are going to use collocation in the next problem. Okay, so where do we get the analytical solution for this problem? Okay, so here's the derivation of the analytical solution, and since I didn't assign this problem, really you can just read a newspaper for a minute until you get to the end. You're going to need the analytical solution for both problems 3A and 4, but derivation you don't really need to follow, but it's interesting, so let's look at it. It's interesting that it's possible to solve with a delta function on the right hand side. So here's your basic problem. The Laplacian of u equals m. That's just the definition of m. The Laplacian of m, in other words, the Laplacian of the Laplacian of u, that's basically u x x x x plus 2u x x y y plus u y y y y. It's fourth order problem, equals minus delta x comma y. That means that's a point source at 0, 0. And u and m are both 0 on the boundary. In other words, it's just simply supported, not clamped. Okay, so how in the world do we solve that? Well, it's obvious that u and m are going to be functions of r only because it's a circle and the force is in the middle and the boundary conditions are the same all around. So u and m should be functions of, in polar coordinates, of r only, not theta. And the Laplacian of u in polar coordinates, if u sub theta is 0, is this. Now that's derived later in chapter 3, but it's well known. Basically, if you expand this out, you'll see this is just urr plus 1 over r u sub r. So that's the Laplacian of u in polar coordinates. That's equal to m. Laplacian of m in polar coordinates is equal to minus delta. Okay, how in the world do we solve this? Well, let's look at the second equation first. Since delta is 0 everywhere except at the origin, that means for all r except r equals 0, where it's infinite, any other r, the right-hand side is 0, so we have this just equal to 0 everywhere except r equals 0, multiplied by r, and you still 0 on the right-hand side. That means that this sub r is 0, which means this r, m sub r, must be a constant. Therefore, m sub r is c over r. And do another integration respect to r, you get c log of r plus d. So there's your general solution for m. Now, since m is 0 at r equals 1, you plug in r equals 1, that's 0, so d must be 0, so the d disappears. But how do we find c? Well, you have to use the divergence theorem to find the c. The integral of delta function over the whole disk is going to always be 1. That's by definition of a delta function. The integral of the delta function is always exactly 1, and you've got a minus in front, so the integral is 1. But now the Laplacian of m is equal to minus delta, so the Laplacian of m integrated over the whole disk is minus 1. But now here's where we use the divergence theorem. See, that's the divergence of the gradient of m, and that's equal to the integral over the boundary of the gradient of m dotted with the outward unit normal, which is partial of m with respect to n. I'm probably losing you on some of this, but look at the appendix A and you'll understand this. So by the divergence theorem, this is equal to the integral of the normal derivative of m over the boundary. Well, the boundary is just r equals 1, and partial of m with respect to n, that's just partial of m with respect to r. That the derivative in the normal direction is just derivative with respect to r, so that's just a constant m sub r at 1 times the length of the boundary, which is 2 pi times r, where r is 1. And since m sub r at r equals 1 is just c, that's 2 pi c, and that allows us to find that c has to be minus 1 over 2 pi. So finally, d is 0 and c is minus 1 over 2 pi, so now we got m. Now we just need to find u from the Laplacian of u equals m. So we go back to the first equation now. That's the Laplacian of u in polar coordinates, assuming u is a function of r only, which it is. And that's equal to m, which is we just figured out, minus 1 over 2 pi times log of r. So first we multiply through by r to get rid of that. Then we integrate, And what in the world's the integral of r log of r? Well, it's r squared log of r over 2 minus r squared over 4. How do I know that? Well, the book tells us, but you can check it. That's a little known antiderivative. Not something you learn in the books, but you can check it easily enough. You take the derivative of what's inside brackets here, you'll get r log of r. So that's the antiderivative of that, of r log of r is this, and you get an arbitrary constant because of integration. Now we divide by r, lose one r there, and that's e over r. Now take the antiderivative of that. Well, there's your r log of r again, and its antiderivative is still r squared log of r over 2 minus r squared over 4. Antiderivative of r over 2 is r squared over 4. Antiderivative of e over r is e log of r, and then we have another arbitrary constant showing up here. Simplify this a little bit. You got minus r squared over 4 minus r squared over 4 is r squared over 2. Factor out the 1 over 2 and the minus 1, and you get this. What are E and F? Well, first of all, the E has to be 0 because at r equals 0, U has to be finite. Plug in r equals 0 here. That's r squared log of, that's infinity, but r squared log of r goes to 0 at r equals 0. So that's 0, that's 0. Well, this would be infinite if E were anything other than 0, and we can't allow that. So E must be 0. And the other F comes from the fact that U is 0 on the boundary. In other words, plug in r equals to 1. That's 0. Well, E is 0. So we just get, that's r is 1. That's 1 over 8 plus F equals, has to be 0. So F is minus 1 over 8 pi. And finally, now that E is 0 and F is minus 1 over 8 pi, we get that. So this is really the only thing you need from, since you didn't have to do problem 3b. I used to assign it, but you'll be glad to know I'm not now. There's the solution to problem 3a. So you need to copy that and compare your solution to that. And finally, I did assign problem number 4, and that is the using the collocation method for the same problem 3a. Except that I just said collocation method doesn't allow a forcing function to be a delta function, but you can approximate it by this bivariate normal function. This thing here, this is the normal function that has a peak at 0, 0 with standard deviation of sigma, so the integral of this is known to be 1, and if you take a real small sigma, it approximates the delta function because its integral is always 1 no matter what delta is, and it's almost infinite, becomes infinite at 0, 0 and goes to 0 everywhere else. So you basically, you can use the collocation method, but you have to approximate the delta function. Now that means it's going to be very, very important to not have a uniform grid. You're going to have to set grid points near, it gives an example here. Suggestion you need to make it very dense near the origin because that's where all the action is. And you're going to have to parameterize your region. Well, that's easy enough because you can just use polar coordinates, and P1 will go from 0 to 1, P2 goes from 0 to 2 pi. You'll have periodic boundary conditions on P2. P2 is basically theta, P1 is R. But you have to make sure you have grid points close to P1 equals 1. Don't use uniform grid points. And should get nearly the same solution as problem 3a. And it should be close to the solution that I just gave you for problem 3b.